It is given a function f of x, and the first part of this question is to find x, y intercepts, asymptotes, and plot a graph. It's quite common questions, so let's start with asymptotes. To find vertical asymptote, we consider or actually we check whether there is division by zero, or whether division by zero arises here, and we can see that we can get division by zero when denominator is 0, so when 3 minus x is 0, so we can see that x is 3 is actually the required vertical asymptote. And how to find horizontal asymptote? To find horizontal asymptote, we should consider x to be very large positive and very large negative, and vertical asymptote, it means that y tends to some value when x tends to plus minus infinity, or in other words, it's actually limit when x tends to plus or minus infinity. And if it looks like this polynomial function, we take into account only the greatest powers of x, y, because when x is very large, 2x is much larger than just x or other powers of x, which is less than the greatest power of x. So when x is very large, positive or negative, y behaves as 2x over negative x, and we can see that x cancels, and we can see that y is negative 2. So y is negative 2 is horizontal asymptote. In general, we should consider plus and minus infinity separately, but here it will get the same when x is very large positive and very large negative. And let's review: when the greatest power of x is greater in the denominator than in the greatest power in the numerator, y is 0 would be horizontal asymptote. It means that the curve falls on x-axis. And when the greatest power in the numerator is 1 more than in the denominator, there will be slant asymptote. When the greatest power in the numerator is 2 or greater value more than in the denominator, it means that the function just always increases or decreases, so there are no horizontal asymptotes. And let's find intercepts. So to find y-intercept, we set x to be equal to 0. So when x is 0, we can see that y is 4 over 3. And let's solve when y is 0, so fraction is equal to 0. When numerator is equal to 0, denominator cannot be equal to 0, so we can see that x is negative 2. So negative 2, 0 is root or x-intercept. And let's plot a graph. Such polynomial functions usually look like a hyperbola. So x is 3 vertical asymptote, y is negative 2 horizontal, and negative 2, 0, and 0 for always 3. And actually it's enough to know these 2 points to plot a graph, because it will be such hyperbola branches. And if you are not sure about quadrants, you may check. How to check? Take for example 10. When x is 10, we can see that it becomes what? uh, or or actually it will be more useful to consider x is 4. You can see it becomes over -1, 11 over -1, -11, and you understand that when x is 4, point is somewhere here, and these dashed lines are like a new coordinate system, and such typical polynomial functions are their graphs are like usual hyperbola. So -2 for always 3. Okay, and now let's consider this more interesting question. It's about self-inversed function. What you may guess that self-inversed is when an expression for just a function is equal to the expression for its inverse. And let's consider a very interesting property which can be used as a property, or can be used to find something, or can be used as a criterion to prove that some function is self-inversed. And first of all, let's consider how can we solve this problem. So it is given some function, and we need find unknown parameter a when function is self-inverse. You may use what definition that function of inverse is x, or inverse of function is x, and since g is the same as inverse, you may substitute just g here. So consider g of g is x. So substitute this for x into g again, and equate it to 0, and solve for a. Or another way, you may find inverse for g and then equate, and also try find unknown a. But let's consider some point AB or xy. It doesn't, let it be AB, which this point belongs to G, and we know that in general for function and its inverse x y change each other. So if AB belongs to a function, BA belongs to its inverse. It's not necessary the function should be self-inverse. It's in general for any function and its inverse. But if it's self-inverse, it means G is equal to G inverse. It means that BA also should belong to just G. And AB should belong to its inverse. So if a function is self-inverse, such points AB and BA belong to function and at the same time to its inverse. And we can use this property. How to use this? We can take any useful point. For example, when x is 0, we can see that y is 4 over 3. So point 0, 4 over 3 belongs to a function, and 0, 4 over 3 and 4 over 3, 0 both belong to function and its inverse. And now we can just substitute 4 over 3, 0 into just G. So, very interesting and important property that AB and BA belong to function and inverse. And you can use this. So here we can just use what y is 0 is a times 4 over 3 plus 4, 3 minus 4 over 3, and just solve for a, and we can see again fraction is equal to 0, so numerator is equal to 0, 4 over 3a plus 4 is equal to 0, and we can see that a is negative 3. And it's the required value for a. And let's review. If function is self-inverse, what is the graph of such a function? And what an example maybe for self-inverse? The easiest example is 1 over x. When y is 1 over x, you can see that the inverse is also 1 over x, and 1 over x is what is usual hyperbola, and we know that inverse is symmetrical about y is x. And we can see our property from a graph. For example, when point 1, 2 belongs to a graph, 1, 2 to 1 also belongs to a graph. It's because it's symmetrical about y-x, and since this graph is also graph for the inverse, also same points will belong to the inverse. And that's all for this question.